Okay, we're going to be talking about a new kind of reaction that you haven't been exposed to before, or you've probably been exposed to them, but you didn't realize what they were. And we're also going to reveal to you today the idea or how the word oxidation number came about. So we've talked about that in terms of when we do ionic compounds, we have to look at these oxidation numbers to determine what the charges are and use that to figure out how we can get our equations to or our molecules, compounds to balance properly. And those oxidation numbers are what we use for that. And today we're going to learn about what oxidation is. So there's a couple acronyms that are very helpful with this. One of them is Leo says GER, which is loss equals oxidation and gain equals reduction. I use oil rig. It's just how I remember it. Oxidation is loss, reduction is gain. And they're talking about in terms of electrons here. Okay. So this is the one I use. You are welcome to use this one. Other people prefer that one, but this is the one that I will typically use throughout the year. All right, so just to summarize so far, we've had precipitation reactions where we have a cation and an anion. They're going to form and precipitate, or an insoluble ionic compound. We also have talked about neutralization reactions where protons are transferred. That's, you looked at your hydrogen, H plus ions to see whether those have gotten transferred, whether you have more hydrogen on this side or this side. Those are your neutralization reactions. That's protons. Redox reactions, then, we are transferring electrons from one reactant to the other. So it's kind of the opposite in a way of these neutralization reactions that we're doing up here. One of the reactants is a metal in elemental form. Okay, so redox reactions, an example of this is corrosion or rusting. So you've seen that out in nature, possibly your vehicle, if it's old enough, probably has succumbed to some of that rusting. So metal compounds by reaction between the metal and some environmental substance, a lot of times, again, that's oxygen. And so that's where that's why they use the oxidation number, because this oxygen was kind of the first one that they discovered caused this. So when the metal corrodes, each metal atom loses electrons. It's going to form a cation. The cation can combine then with an anion to form an ionic compound. So we have to have an oxidizing agent in one that promotes oxidation, which oxygen is a great one because, and it's easy to remember because that's kind of in its name. So it's going to lose electrons. Oxidizing agents achieve this by accepting electrons themselves, and in the process they become reduced. Reducing agent then is one that promotes reduction, one that can cause a species to become reduced by gaining electrons. Reducing agents then achieve this by donating electrons to the process, and they become oxidized. So oxidation. When an atom or an ion or a molecule becomes positively charged, it's going to lose electrons. That means that it's oxidized. So loss of electrons is called oxidation, or OIL. Oxidation is loss. The first reaction studied, again, involved oxygen, and that's where they ended up getting the term oxidation from. Reduction, then, an atom or an ion or molecule becomes negatively charged, so it's going to gain electrons. It's going to be reduced. So gain of electrons is reduction, or reduction is gain for the oil rig analogy that I use. Okay, here are some examples of oxidizing agents, and we'll talk more about these, and some reducing agents as well. So here we have chlorine. Anytime you have an element that is just by itself, a diatomic element or an element by itself, it has the oxidation number of 0. This, they give us the charge on it. It is a -1. So chlorine went from a 0 to a -1. It ended up gaining electrons to become more negative, so that chlorine was reduced. Reduction is gain. Manganese, then, here. Typically, oxygen is a -2 in almost all cases. There is one exception, one big exception, and that's peroxide. So when you have a peroxide going on, it's going to be a -1. Otherwise, almost all the time, oxygen is a -2. Okay, so we need to look at this element here. Okay, so we're going to kind of draw a T box here. We have -2 times 4 is a -8. We have a negative value here. So we have a negative charge on this whole thing. So if this is a -8, this has to be a +7. So manganese is a +7. Our hydrogen here is a +1. It's given to us. Over here, manganese is a +2. So manganese went from a +7 to a +2. If it did that, it had to gain electrons to become less positive. So if it gained electrons, then it was reduced. Okay. Our oxygen here stayed at a -2. This stayed at a +1, so nothing happened with that, just with the manganese. You can also go back. You've got some homework to practice on these problems. So if you look at this, for example, and we want to know, and I'm just going to do, not just the underlined one, but I'm going to do all of the substances here. So let's look at this one over here, our copper right here. If we look at that, we're going to split this up into two groups here. Okay. This right here is going to have an overall charge. Let's see if we have an overall charge here. We have one of these, we have two of these. So this must be a -1 because this was a +2. That's how they got that 2 here. And we have two of them. So this side of the equation has a -1 charge. Now, if we look at our oxygen and our bromine, if we break those down further, and we want to know the charge on bromine here. Well, oxygen has a -2 charge. So -2 times 3 is a -6. Between these two things, I have a -1 charge. So my bromine has to be a +5 for its charge. Go over here. Look at this one, sodium carbonate. If I look at this, my sodium has a +1 charge. My carbonate overall has a -2 charge. So if oxygen has a -2, -2 times 3 is a -6. My carbonate ion has a -2 charge, so that means the carbon has to have a +4 charge. So you need to get very, very, very comfortable with determining the oxidation numbers from these, and you cannot use a periodic table to do it. First of all, the periodic table that they give you will not allow you to do that. Second of all, you need to be able to figure this out on your own. You're not going to be able to have a periodic table at your disposal to be able to make it happen. So up here, let's try another one. We have, again, zinc. Because this was a 2 over here, our zinc has a +2 charge. Our nitrate, then, the whole thing has a -1 charge. But if we're trying to figure out between the nitrogen and oxygen what their charges are, oxygen, again, not a peroxide, so it's going to have a -6. My overall charge on the nitrate ion is a -1, so the nitrogen has to be a +5 because +5 -6 gives me a -1 charge. Let's see if we have a few other ones down here that might be kind of fun to do. Here, this one might be kind of fun. We have a bunch of different things going on here. Okay, so my sulfate ion over here is the overall charge is a -2. My ammonium ion here is a +1. So if we want to figure out the overall charge for each thing here, hydrogen's always a +1. So +1 times 4 is a +4. And if I look at my nitrogen, then this whole thing has to have a +1 charge. So nitrogen has to be a -3. Over here with the sulfate, if we look at that, my overall charge for sulfate is a -2. Oxygen being a -2, -4 equals a -8. Overall charge is a -2, so my sulfur has to be a +6. Here, if we look at this guy, we look at our aluminum and our chromium and our oxygen. 3 down here, which means aluminum was a +2. My chromium, because of this 2, was a -2. I'm sorry, this is a +3. There we go. This is a -2 over here. Oxygen always a -2 unless it's part of a peroxide. So -2 times 4 is a -8. I need an overall charge of -2 here. So because of that, that's going to make this chromium a +6. Let's see here. Try to find another one that's a little more challenging. Oh, here. This is a good one, the phosphorus, okay? Phosphorus and oxygen. So again, oxygen's a -2. So -2 times 5 would be a -10. Over here then, this doesn't have a charge associated with it. So this side has to be a +10. But this phosphorus has a 2 down here. So when I go back up, I have to divide by that 2. So that means that the phosphorus is a +5. So hopefully you're starting to get the hang of things as far as these oxidation numbers are concerned. So let's go back over here. You can see where they got these. Again, zinc here is a 0 because it's by itself. This hydrogen is going to also be a 0, and this tin is also going to be a 0. This is a +2. So if zinc went from a 0 to a +2, it had to lose electrons. And remember that oxidation is loss, so zinc was oxidized in this process. All right, again, we determine if an oxidation reduction reaction has occurred. We have to assign those oxidation numbers to keep track of electrons. Oxidation numbers apply to each atom. And like I was showing you in the previous Word document, when we have a neutral atom, it's 0. Diatomic molecules, your Brinkelhoffs, they're also going to be 0. And then the monoatomic atom is going to be the same as its charge. Nonmetals tend to have negative oxidation numbers. Oxygen has a -2, except in the peroxide ion. And I have seen that on the AP exam before, so be very, very, very careful with that. In which an oxidation number of -1. Hydrogen is a -1 when bonded to a metal, a +1 when bonded to a nonmetal. Fluorine is always, no questions asked, no arguments, no other definition. It has to be a -1. All other halogens have an oxidation number of -1 when they are negative, but can have positive oxidation numbers, so be very careful with those. So if we look at this example, they have another way of doing it. So if you're comfortable, if you want to look at the way that they're doing it and do it a different way, that's fine. This is the way I do these. So I have my K2Cr2O7. I'm going to split my metal and my non-metal, my polyatomic ion over here. This ends up being a, because of the charge, this ends up being a -2. I got that from here. So if I have 2 of these, that means that I have to have a +1 here. Okay. So, so this was remember we had a +1 over here. This overall thing down here was a -2. That's our goal, is to get this side to a -2. So I need 2 of these to get this up to, or +1, because I've got 2 of them. That'll be a +1. Okay. So then let's look at this. If we split this guy down and we look at our oxygen, we want a -2 here. So that's a -14. We need an overall charge on this side of a -2. So that means that I've got -12 over here. 12 divided by 2 then is, I'm sorry, that would be a plus. That would make this a +6 then for this guy. Okay. Then if we look at our next problem, if we look at some of our oxidation numbers again here, it looks like some of these got kind of off kilter. So I'm going to move this one over here. So Al2SO43. My aluminum then is going to be a +3. My sulfate over here, overall charge for sulfate is a -2. So -2 is my overall. Remember, oxygen is a -2, so that would make that a -8. That I need an overall charge of a -2, so that makes sulfur a +6. Okay, over here, this is sulfur dioxide here. So again, oxygen is a -2, so that makes this side a -4. This side has to be a +4. +4 divided by 1 is a +4. Over here, we have our mercury sulfite. Mercury and the sulfite is a -2. This makes this a +2 then. So sulfite, I have a -2 times 3 is a -6. I need an overall charge on that side of a -2, so this has to be a +4 over here for my sulfur. This is ClO3 is a -1 charge. The CD then has to be a +2 charge. So then if I want a -1 charge overall on this side, my oxygen again, -2. -2 times 3 is a -6. My overall charge is a -1 for the polyatomic ion. So that means that the chlorine has to be a +5. Here we have sulfur. So sulfur has to be the hydrogen, since this is with a nonmetal, our hydrogen has to be a +1. So I have a +2 charge on this side, which means that this guy has to be a -2 over here. S8, this is a single element by itself, so its oxidation number is 0. Na2SO3, SO3 is an overall charge of a -2. If oxygen is a -2, then -2 times 3 is a -6, so our sulfur has to be a +4. Our sodium over here, if we had a +2 on this side to balance out that -2, then we go up, we divide by 2, so it would be a +1. And then lastly, if our chlorine is a -1, -1 times 2 is a -2. -2, that means this side has to be a +2, so our sulfur is a +2 charge. So oxidation reactions are going to have changes in oxidation numbers. You're going to see that you're going to increase your oxidation number because it's going to lose electrons. Reduction decreases oxidation number because it gains electrons. So again, this is the one I use. You're welcome to use Leo Goes Grr if you would like. It's completely up to you. So if we had a reaction like this, okay, if we're looking at this, we're trying to tell whether this is a redox reaction or not. Well, my potassium is 0. My chlorine is also 0 because they're elements by themselves or a diatomic element. So when I go over to this side and I look and see what's formed, well, my chlorine is a -1. My potassium is a +1. So if K went from 0 to a +1, to become positive, it had to lose electrons. So it's going to be the item that was oxidized. So it'll go through oxidation. My chlorine went from a 0 to a -1, so it gained electrons. So it was the item that was reduced. So that's how we figure out oxidation versus reduction. You can also look and see how they've done it down here. If you prefer this method, that's fine as well. You are going to need to be able to break these out and do these half reactions, be able to see that potassium here became positive because it lost an electron, and chlorine gained 2 electrons, and that became negative. All right, oxidation number is the number of electrons that an atom loses or tends to gain when it's involved in a redox reaction. If the atom gains or tends to gain electrons, then the oxidation number is negative, and vice versa. If there's no change in the number of electrons, then it hasn't taken place in the redox reaction. In that case, then it's equal to the ionic charge. And in the case of covalent compounds, where the oxidation number may be regarded as the charge that the species would have if the compound were fully ionic. So rules that simplify our assigning of oxidation numbers. The oxidation number of an element when uncombined as a free element is always 0. Sum of oxidation numbers in a neutral substance has to be 0. An ion, the sum of the oxidation numbers has to equal the ionic charge. Some elements exhibit very common oxidation numbers. Group 1, always +1. group 2, always +2. Fluorine, always, always, always -1. Oxygen, always -2, except with that peroxide ion. And then hydrogen is almost always a +1. Binary compounds, group 17 elements, that's your halogens, are -1 typically. 16 are typically -2, and -3 for group 15, not always though, so be careful. So in the redox reaction here, which species is being oxidized and which one is being reduced? So if we look at our silver here, it has gone from a +1 here to a 0. Our aluminum went from a 0 to a +3. So if silver went from a +1 to a 0, that means that it gained electrons. And if it gained electrons, reduction is gain, so it was reduced. Our aluminum went from 0 to a +3, so it became more positive. It lost electrons, so it was oxidized. So they wanted us to assign oxidation numbers here. O2, the oxygen would be 0. HF, this is a -1, so your hydrogen has to be a +1. Again, -1, +1, 0. This is a +2. The sodium here is a +1. Chlorine would be a -1. -2 for the oxygen, +1 for the hydrogen, and -2 for the oxygen, +2 for the magnesium. So if we look at oxidation of a metal by acid, you can see here that we have zinc, we have our acid here, hydrobromic acid, and we're forming zinc bromide and hydrogen gas. So if we look at what's being oxidized and reduced, our zinc is starting out at 0 here because it's by itself. It's not in a compound, so its oxidation number is 0. If we go to the other side here, we can look at bromine, which is a -1. -1 times 2 is a -2. So that means zinc has to be a +2. So zinc has gone from a 0 to a +2. So it's become more positive. It has lost electrons. And remember our acronym OIL RIG. So it has lost electrons. That means that zinc was oxidized. All right, let's see what happened with our bromine and our hydrogen here. Over here, if we look at bromine, that is a -1. That means that our hydrogen has to be a +1. So we went from a +1 to a 0 over here. So our hydrogen went from a +1 to a 0, which means it gained an electron because it became more negative. So that means that it was reduced. If we write this out in terms of reactions and how these reactions are occurring separately, and this is something you're going to have to do when we get into second semester, so you need to get comfortable doing that. We would look at our zinc, and our zinc would have gone from here to zinc 2+, plus it gave off 2 electrons. And these electrons are going to become very important when we get into Unit 9, when we're looking at how many electrons are given off, because that's going to determine, we're going to put that into a equation, and we can determine how much electricity is moving through our different cells. If we look at our hydrogen here, our hydrogen is a +1. We would need to have 2 of those. So 2 hydrogen plus 2 electrons is going to give us H2. All right, oxidation of metals by salts. So here is our iron. Our iron has a 0 oxidation number. Over here, if we look at this one, iron will be a +1 because our nitrogen over here is a -1. I'm I'm sorry, iron would have been a +2, excuse me. So iron is a +2 because this was a 2 for our subscript up here. So that would have made that a +2. This is a -1 overall charge for this guy. So if we're looking at our nitrogen and our oxygen over here, -2 here, -2 times 3 is a -6. So this has to be a +5 for our nitrogen, and our nickel is a 0. So over here, our nickel is a +2. And if we look again at our nitrate ion here, our overall charge for our nitrate is a -1. That's its atomic number. Not atomic number, but oxidation number for nitrate. So if we have our oxygen at a -2 times 3 is going to end up being a -6. So that makes our nitrogen a +5 again. So there's been no change to our nitrogen at all. There's been no change to our oxygen either. So it's the iron and the nickel that we're looking at as far as changing. So if you look at just the iron went from a 0 to a +2. So it has become more positive. It lost electrons. And our oil rig tells us that a loss of electrons is oxidation. Our nickel then went from a +2 to a 0. So it has gained electrons because it has become more negative. So it was reduced. If we look in terms of ionic equations here and splitting these out into half reactions, our iron went from a 0 over here to being iron +2 plus 2 electrons. Those 2 electrons then were picked up by our nickel. So our nickel was a +2 plus 2 electrons is going to give us nickel over here. And so these are our half reactions. And like I said, they're going to become vitally important when we get into Unit 9, and you're going to need to be very, very, very comfortable with doing these. So if we look at our next problem here, this is oxidation of metals by acid. We're going to look at our oxidation numbers and figure out what's being reduced and what's being oxidized. So for our aluminum here, it has a 0 oxidation number. It's not in a compound, it's by itself. This hydrogen has a +1. The bromine has a -1. This hydrogen's by itself, so it has a 0. Our aluminum then has a +3, and our bromine has a -1. So if we look at our aluminum, it went from a 0 to a +3. So if we went from 0 to +3 here, then that means that it's lost electrons. And if we look at our oil rig, loss of electrons means that it was oxidized. Okay. So now we need to find out what was being reduced. Our hydrogen went from a +1 to a 0. So if it went from a +1 to a 0 over here, that means that it gained electrons because it became more negative. And a gain of electrons means that it was reduced. Okay. Our bromine was unchanged. It was a -1. It stayed a -1. So if we look at trying to write these equations out in terms of getting them, a lot of times when they give you these equations, they don't have coefficients in front of here. So we're going to kind of pretend that these coefficients aren't here, and then we can see what's going to happen in terms of our electrons. So if we break out our aluminum, so our aluminum is here. It has all of its electrons with it. If we go here on the other side, that aluminum becomes a +3, which means that it had lost 3 electrons. And since it lost 3 electrons, that means that it was oxidized. Okay. Then if we look at our hydrogen here, our hydrogen went from a +1 on this side over to it's doing it again. Darn. Over to H2 over here. Now, since this is H2, we would need 2 of these to get us H2 on this side. It's also going to have added in 2 electrons to get us to that, okay? So the problem is that this gave off 3 electrons and this has 2 electrons here. So we have to get this equation to balance. So what we need to do is we're going to need to find the least common multiple between these 2 values. And the least common multiple between these 2 would be 6. So we're going to multiply everything in this equation by 2. We're going to multiply everything in this equation by 3. So our half reactions, when we break these out, we're going to have aluminum. We're going to have 2 of those. Yields, we've got 2 aluminum on this side with a +3 charge, plus now 6 electrons. Those 6 electrons then are going to be picked up down here by this hydrogen, okay, because 3 times 2 is 6. That's going to give us 6 hydrogen ions and give us 3 times 1 is 3 H2. And so everything then balances out. So if we wanted us to write down our half reactions, this is what that would end up looking like, okay? So let's look at another one here. We have magnesium. We have iron 2 chloride. So our magnesium has a 0 oxidation number here. Over here, it's going to have a +2. Our chlorine then has a -1 here and here. Here, the iron will have a +2, and this iron will be a 0. So our magnesium has gone from Mg, it's gone from a 0 to a +2 status, which means that it had to lose electrons to become more positive. So lost electrons means that it was oxidized. Our iron went from a +2 to a 0, which means it became more negative. So it gained electrons. So that means that it was reduced. If we look at the half reactions for these, we would have magnesium. Magnesium is then turning into a magnesium ion, and it's giving off 2 electrons. Those 2 electrons then are being picked up by the iron. And then that becomes iron on this side. So that's the half reactions for these. Let's try one more. This wasn't in your packet, but I want to try one more just to kind of show you how it works. So let's look at copper. And copper with nitric acid. Oops, sorry. I shouldn't have done that arrow yet. So plus H plus yields Cu 2 plus NO plus H2O. All right. So if we look at our oxidation numbers here, our copper on this side is already given to us as a +2. This would be a 0 on this side. Over here, we have hydrogen as a +1. We also have hydrogen as a +1 right here. If we look on this side, our hydrogen again is a +1. Our oxygen is a -2 over here. Here we've got oxygen as a -2, so that means that this nitrogen must be a +2. If we look at our nitrate itself, the overall charge for the nitrate is a -1 charge. So if we have a -2 for our oxygen, that's -6 on this side. We need an overall charge of a -1. So this nitrogen has to be a +5. +5 divided by 1 is a +5. So if we look and see what's oxidized here, we've gone with our copper, has gone from a 0 to a 2 plus, which means it became more positive. So it lost electrons. So it was oxidized. Our hydrogens are unchanged. Our oxygens are unchanged as well. But our nitrogen has gone from a +5 to a +2. So that nitrogen then, has then been reduced because it gained electrons. It became more negative. So if we look at our reactions here of just the copper, we have our copper. It is going to be giving off 2 electrons and becoming Cu2 plus. Those 2 electrons then will be picked up, but we can't just as easily go back, do this as this one where we had the 2 electrons to here, because if we look at the nitrogen, it didn't trade out 2 electrons. It ended up gaining 3 electrons. So that doesn't work. So we've got to do these separate half reactions. We're going to have to multiply by a common multiple for this as well. So let's look at nitrogen separately. So our nitrogen went from a +5. That +5 gained 3 electrons. Gained 3 electrons, and it became nitrogen with a +2 charge. So now we need to look at our least common multiple. We are going to have to get this least common multiple for our electrons. We need to multiply these through, and this time the least common multiple again is 6. So I'm going to multiply this equation by 3. I'm going to multiply this equation by 2. That will get me to where I need to be. So I'm going to have 3 copper yields yields 6 electrons plus 3 copper ions. This guy down here, I'm going to end up with 2 nitrogen, 5 plus. I'm going to, oh, wait a second, shoot. Plus, I need to do my 6 electrons here. And then that gives me 2 nitrogen ions on the other side with a +2 charge. Okay, so by doing that, we've taken these 6 electrons that copper gave up, the nitrogen picked those up and became this form of nitrogen. And when we get into batteries, we're going to be, and electro cells and stuff like that in Unit 9, these electrons really come back to us and come into play. Okay. Again, just kind of a recap between acids and bases. We had our acids. They were proton donors. These are electron donors and receivers. So that's the difference between our oxidation reduction reactions and our neutralization reactions. Okay. Again, there's different types of redox reactions. We can have single displacement, where we end up with, and you can see that happening here with the halogen being replaced. We can have a combustion reaction where we're burning in the presence of oxygen. Other combustion reactions here. And then we talked about acids and bases earlier, where we had proton donors and acceptors. So if we go back and revisit our net ionic equations, we need to kind of bring together some rules now that we understand redox reactions. So in a net ionic equation, any strong electrolytes, soluble ionic compounds are written as dissociated ions. Strong acids and bases are written as dissociated ions, but weak acids and bases are not. So be very, very careful. Ions then that are reduced or oxidized are also written as dissociated ions. And so this is the one that I wanted to come back and kind of shore up and make sure that you recognize that. So those ions that are reduced or oxidized are written as dissociated ions.